Hello everyone, thank you so much for coming. I think today will be our last lecture for this semester, so we'll cover security at the network layer, the IPsec. So 2 weeks ago we covered the security at the application level, right? So we spoke about pretty good PGP, and last week we spoke about security at the transport layer, SSL and TSL. And today we're going to talk about IPsec, right? So providing security at the network layer. All right. So just we're going to give you an idea. We are not going to go in deep details, and the details in the textbook we could go over it. We're going to define the architecture of IPsec, IP security, to discuss the application of IP security in transport and tunnel mode. There is two modes. One is transport and one called tunnel. All right. To discuss how IPsec can be used to provide only authentication. Okay. And to discuss how IPsec can be used to provide both confidentiality and authentication. There is two modes. To discuss security association and explain how it is implemented in IP security, and to define internet key exchange and explain how it is used by IPsec. So basically, in TCP/IP protocol suite, as you know, starts from the physical data link, network layer, transport, and application. So we are trying to provide IP security at the network layer. So IP security is designed to provide security at the network layer, Okay. Usually in the network layer, usually in the application or transport, we could provide end-to-end security. So we encrypt at one end, and the data will gonna go through many hops, all right, to the end. So what we secure at one end will be revealed at the other end. It will be end-to-end security. In the network layer, it does not happen, because in the network layer, the communication is not end-to-end. It will end to hop, or point to point. So the data will go from host to a router, from router to another router, okay, until the end, from router to host, right? That's how it is, right? That's what is in the IP level, right? Because it carries the IP address. So every hop it goes to, it's gonna change the IP address. So when we have, for example, source in here, gonna go to a router, then it goes to another router, let's say third router, and we're gonna go to host, right? So the packet, okay, let's take going like that, the data is going like that. So the packet when it moves from here to here, it has a source address and destination address. So what's the source address at the first step? S, let's call it 1, 2, 3. And what's the destination address? R1. Then here, what is called R1, R2. Then here R2, R3. Then R3, and the destination H. We call it H there, right? So as the packet moves, the header, IP header changes, the IP address changes, right? Right? So it keeps, so it's kind, when it's received by R1, it's gonna read the header and change the source address and destination address. So we're looking for the security now only through these links. But in the application layer, it will be from host to host. So when we have like data, for example, at the application layer, data, okay, data or payload is payload, load, okay, and the header, all right, this will be secured from here to here, okay, to be secured from end to end. That's the difference. And transport end to end, but in the network layer, okay, it cannot be end to end. So there's two modes. IPsec operates in one of two different modes, transport mode and tunnel mode. Let's take a look. So let's start with the transport mode. In a transport mode, IPsec protects what is delivered from the transport layer to the network layer. Here. So you see in here, this is the transport layer payload. Okay, it's gonna move here. We're gonna add IPsec header and IPsec trailer. All right, and then everything in here, from here to here, gonna move as IP payload. IP payload. Everything will move in here. So the IP header is not protected. It's not protected. It will be sent as a plain text, right? Again, so this is the transport mode. What we do, we take the payload from the transport, all right, the transport layer, and we insert it like a sandwich between the IP header, the IPsec header, and the trailer, okay? And then everything in here will be encrypted and put as IP payload, and the security only for the payload. It does not include security for the header. Clear? All right. So IPsec in a transport mode does not protect IP header. The IP header is not protected. The only thing protected is the payload. The payload coming from where? Transport layer. From the transport layer. Okay? So it only protects the information coming from the transport layer, as you see in here. Alright. So in the transport mode, what will happen? Again, you have the transport layer. The transport layer by itself has the data, has two parts. Has the payload of a transport layer and the header of transport layer, right? Right? So every level has a data and header, right? We keep adding header. So this is the payload and this is the header for transport layer. All of it will be included in as a sandwich in the IPsec layer. We have a header and we have a trailer, and everything in here moving here. And then everything will move to the network layer. So what will be on the wire will have the payload in here and here, and the IP header is not protected. So IP header is like plain text, anybody can read it. Why everybody has to read it? Because that's what we said, when it moves from one hop to hop, the header needs to be changed. Keep changing. If you encrypt it, nobody can read it. It cannot move anywhere. Right? Alright, so the network layer packet, virtual communication and the network layer. And when it comes in here, so we receive this in here, we're going to go to IPsec layer again, okay? And of course, what we did in here, like for example, authentication or encryption, whatever, it will be reversed. And then again, we'll be able to read the data, the header with the trailer, and the payload will move off to the transport layer. So that's what we call a transport mode. Transport mode. Why is transport mode? Because we take the payload from the transport layer, and what we do with it? Protect it. And add to it a trailer and header. That's it. Transport mode. Very simple. Alright? The tunnel mode is a little bit different. So in the tunnel mode, IPsec protects the entire IP packet. Entire IP packet includes what? The header. Includes the header. So somebody say, how can I protect the header? If I encrypt the header, the data cannot move because it has to be read at every stage, right? We'll see how we do that. All right. So the tunnel mode, IPsec protects the entire IP packet. It takes an IP packet, including the header, applies IPsec security methods to the entire packet, that including the header, and then adds a new IP header. Aha! So we'll take the original IP and we encrypt it, but we add a new IP header. So we're gonna have two IP headers. So IPsec tunnel mode protects the original IP header as well. So what will happen? Look in here. So what we do, this is at the network layer, right? That's the IP payload and that's the IP header. Normal, right? That's without any security. Usually that's what we'll have. So what we do, we take the whole IP packet, which includes the payload and the header, we passed in here. We're gonna add another header and a trailer, right? And everything encrypted and all of that passed in here. And then we don't put the old IP header, we create a new IP header. So there is an old IP header included with the data, protected, and there is a new IP header. So we copy the information that we don't need it, hidden, like the IP address, we put it in the IP header, but everything else will be protected. Everything else will be protected. Okay, so that's what happens in here. In the tunnel mode, can we create a tunnel? So this is the network layer, right? We moved it here with header and trailer, and we added a new IP header. So we have an original IP header, a new IP header. That's what you do in the virtual communication. When you try to transmit it, it will be received by a router A, router B. The header will be read and discarded, go up. It will be reverse operation then here, and then you have the new layer. So the router basically will be able now to read the original IP header. Will be able to read the original IP header. Again, remember in the IP packet will move from node to node, from host to router, from router to router, from another router to router, and so until it goes to the host. So every step, what does it have to do? It has to change the destination address. It has to change the destination address. All right? Okay? So if I encrypt the destination address, then nobody can know where it will go, right? So that's what happens. So basically, the transport mode versus tunnel mode. This is transport mode, so start from the application layer data. So the application layer has what? Has payload and header. All of it gonna go where? To the transport layer, which has data and header. Now we're gonna pass to the IPsec layer and then to the network layer. So it's like, but the header in here is not encrypted, it's not protected. In the tunnel mode, again, application, transport, network layer, normal. Then we have the IPsec layer, then we have kind of a new network layer. So we have two network layers. Okay, two network layers. All right. So in your opinion, which one is much more secure, this or this? Tunnel, because you also protect. So two security protocols. So how many modes we have? Two, transport and tunnel. Okay, now there's two security protocols. So IPsec defines two protocols: the authentication header (AH) protocol and the encapsulation security payload (ESP). So what are the protocols? AH and ESP. So two protocols, and we have two modes. So in total, how many combinations we could have? Four. We could have up 4 combinations, right? To provide authentication and or encryption for packets at the IP level. Okay, so let's start with the simple one: authentication header. Authentication header. So the authentication header protocol provides source authentication and data integrity, but no privacy. When we say but no privacy, that means no encryption for the data. Okay? We're providing only source authentication, that we authenticate the source. So if the data is coming from node A, we know it's A, authenticated. And data integrity, that means data is not changed. So we authenticate the source and we authenticate the data, right? Only. We don't make sure it's a private. We don't privatize it. We don't encrypt it. All right? All right? So what will happen in here? So this is the authentication header. So data used and calculate. Okay. So what you do? That's how you form it. So you have the original data packet. You add a padding. Okay. Then you insert the authentication header with the IP header. So the IP header will stay as it is, not encrypted. The data in here also not encrypted at all. It's not encrypted at all. So nothing is encrypted. Not the IP header, not the data, original data, nothing is encrypted. What we do, authentication. For authentication, what we do? We create a digest, right? That's what we do for authentication, right? We create a digest, we send it, that receiver will create the digest, compare it. If the same digest, then there's authentic, right? So in the header, what we do in here, okay, we'll have next header. This is the next header, okay? What is next header? It will have the header description in here. We moved it in here. So in the IP header, in the first field, that tells you what kind of header is it, what kind of packet is it. Is it TCP packet? Is it UDP packet? You know what type of it is, right? So whatever type in here gonna move in here, then payload length reserved, then security parameter index. This is like kind a path, like a kind of a path address. So for example, you know, if we're gonna go, for example, to southern New Jersey, for example. So I start from here, route 8, then route 15, then route 95 to go south in New Jersey. So instead of naming it like that, we'll give it a number. This is route number 15. That's what it is, security parameter index. So all the packets will go through the same path, right? And then you have the sequence number. So all the packets will come in sequence for one connection. Why? Because some packets will arrive before the other, so it will be arranged. And then the authentication data, the digest. So what you do, you create a digest for the data from here to here. So that's the hash function, and the digest created will be added to here. Will be added to here, right? So data used in calculation of the authentication data, except those fields and IP header changing during the transmission. Okay, so you don't include them. Why you don't include them? Because you're gonna change in the transmission. So if you include them in the hash calculation and the packet arrives there, you gotta calculate the hash again. They'll not be equal because changed. So things change in the IP header, you don't include it in the authentication. You agree? All right? So that's what it is. So that's the again. So what we did in here, okay? What we did, we took the transport layer information, and we have to add authentication header. So this is the data. We add a padding to, and then we have the IP header. Then we calculate the authentication for all the data except the change in parameters and the here. Okay. So this is protocol for the encapsulating security payload. Okay. Okay. It provides source. It provides three things. Provides source authentication like AH, data integrity like AH, and privacy. That means the data will be encrypted. Data will be encrypted. So which one is more secure, ESP or AH? ESP. Why do you need AH?
Because it's
Huh?
has a lower overhead.
What?
Your overhead will be lower.
No.
That's only age will be changed, data is
No.
not changed.
Actually, we don't need it. We don't need it. But this AH implementation came before. And many commercial products use AH, so it's still available. Alright? But technically, if you can provide, so AH provides authentication and data integrity. And this associated privacy, use this as well. Alright? Alright, but it's, you know, it's available. It's AH came before, and it's still available there. Alright. So look how this works, the ASP. Okay? So what we will do, you will have two, we have a header and trailer. Remember in here, just we have one part added in here. In here, you'll have the IP header will stay in here. Then you have the header, which is 32 bits. You're gonna have security parameter index, and you're gonna have the sequence number on it. In the trailer, what you're gonna have a padding. So the padding in here added in here, right? Now the padding is added to the trailer, and then you have the pad length, the padding length, and the next header in here. Next header in the previous one, where was it? Here. So it moved in here. Moved in here now, right? So what will happen? The data with the trailer will be encrypted. Will be encrypted. And the header with the trailer with the data will be authenticated. Authentication means what? Calculating the digest and adding it where? Where? Yeah. Authentication data. Okay? This is authentication data. In the previous where we added it? Here. Right? We added it here. Okay? So it was added here. So we're gonna have encryption. So the data from here to here encrypted. That means it's privacy. So in here what we provided, source authentication, message integrity, and privacy. Privacy for the data. IP4 and IP6. IP6 support both IP4 and 6. IP6, however, AH and ESP is part of the extension header. If you need to compare the AH and the ESP protocol was designed after the AH protocol was already in use. ESP does whatever AH does with additional functionality, which is privacy, providing privacy. So the question, do we need it? We do need to use AH? You don't, but it's there, you have to know, because some commercial applications, they use it. Alright? So if you need to compare them, the IP6, the services, so access control, both of them provided. Message authentication and message integrity, both of them provided. Integrity, entity authentication, like data source authentication, both of them provided. Confidentiality, ESP provided, AH does not. Replay attack protection, both are provided. Alright? Both provided. So to prevent replay, we created like a window. Remember in DCC when you learned about receiving window and sending window? Alright, in the transport layer, you remember? That the data is divided into packets, okay? And you'll have a window. So you cannot, this is a window, for example, the size of the window is W, starts from N to N plus W minus 1. So if you receive a packet before, outside the window, so let's say list N number 3, and list W is 5, okay? The size of the window is 5. So 3 plus 5 minus 1, how much? 7. So that means at the moment I can receive a packet with a sequence number 3 or 5 or 6 or 7. Alright? Or 7. If I receive anything before that, I'm gonna throw it. If I receive anything after that, what will happen? I'll move the window. Okay? So let's say I received, if I received now packet 9, so this has to go 2 steps. The window gonna go 2 steps further. Right? You understand the windows, right? The window, the receiving and transmission window. We took it in DCC, right? Okay, refresh your memory if you forgot. Okay, so basically to prevent replay, we create a window. So we have to receive a packet within this window or after. Alright? So our example, if I say this is 3, and this will be 2 plus 3 plus 5 minus 1, 7. So the window is 7. So I could receive 3 or 4 or 5 or 6 and 7. If I receive number 2, what will happen to it? Discarded. Discarded, it's outside of the window. If I receive number 8, what will happen? The window will move. Alright? How about if I receive number 10? The window will move to 10. Alright? But if I receive after that number 3, what will happen? Huh? Discarded,
Yes.
because I moved the window. Alright? Alright? Clear to you? Yeah? So there is a window, receiving window. So that's the basic idea. That's the basic idea of you know, the IPsec. Then after that, we have something called security association. Security association. All right. So what is security association? So you understand the concept of IPsec. So we have two modes: tunnel and transport. Right. In the transport, we don't protect the IP header. In the tunnel, we protect the IP header. Right. And there is two protocols. Okay, which is authentication header and ESP. Right? Just different format. The first one, the AH provides secure source authentication, message integrity only. The second one provides privacy on top of the previous ones, and they work in a system. That's how they designed. It's like when you drive a car. When you drive a car, there's a gear, right? Gearbox, right? So when you put a D, it goes forward. You put R, it goes backward. N goes nowhere. All right. Why? It was designed like that. Okay, it was designed like that, right? All right. All right. So this works like this. It designed like this. It was just you have to understand how it works. Okay. So let's talk about security association. So security association is a very important aspect of IPsec. IPsec requires a logical relationship called a security association. So, between two hosts. This section first discusses the idea and then shows how it uses IPsec. Okay. So you have remember in the network layer. It's not I'm gonna say it for the 100th time. It's not end-to-end security. It's point-to-point security, right? It's not end-to-end security. So the data has to change. The IP header changes from point to point, right? So when you look in here, for example, okay, so Alice would like to communicate with Bob, and this is the message. So there is association between them. So they're gonna use, for example, the algorithm this, and the key is whatever key, right? So this is called outbound security association. The receiver and the sender has to know what algorithm for encryption gonna use, and what is the key, right? So they have to get associated. They have to know these for each other, right? So that's what we call outbound security association. And this is inbound security association. So how we can create this association? Association is simply that we know each other. We know the parameters we're gonna use, the language we're gonna use, the encryption technique we're gonna use, the key. That's what is security association. So whatever at the sender we call it outbound security association, and at the recipient we call it inbound security association. Clear? What is security association? Is the data that we need to know before we can communicate. Okay? Example, the algorithm and the key. And there is two kinds of security association. Outbound and inbound. Simple so far, right? So when you look in here, security association, SAD, it's like a database, all right? So for example, when you look in here, for example, it will have SPI. What is SPI? Security parameter index. Okay, security parameter index. Okay, DA, what's DA? Destination address. And P, the protocol. What kind of protocols we have? AH or ESP, right? So security association here. So for example, it will include the MTU, the maximum transmitter unit, the mode. What kind of modes we can have? What mode? What kind of mode?
Transport mode.
transport or
Tunnel.
tunnel mode. Okay, and other parameters that they need, right? So they have to, so SPI is the security parameter index, the destination address. So this is database in one of the nodes. So for example, it's saved in Alice. Alice can communicate with how many people? Many people could communicate with Bob and many others. So let's say the first line for Bob. So it will tell you the security parameter index, the destination address will be Bob, the protocol used, and other parameters, and many other nodes, right? So the SPI is security parameter index, the DA, the destination address, AH or ESP, which is the information for either one, in here. P is the protocol, where is P? Yeah, protocol. And mode, IPsec mode flag, and SN is the sequence number, OF overflow flag, and empty replay window. What is the size of the window? Like in our example, it was 5, for example, right? And LT is the lifetime, and MTU the path MTU is the maximum transfer unit. Remember that the data could have a maximum. So this is if this table stored in Alice, what do we call it? Outbound.
Security.
Okay. If it is stored in Bob, what do you call it? Inbound security association. So this is special SA parameters that we spoke about. I mean, just take a look at that. That's so let's take one or two. For example, SA lifetime. So this defines the lifetime for the security association. Bless you. So when you create a security association, it has a lifetime, right? It does not stay forever. It has to be renewed. Let's take a look at, for example, path MTU. MTU is a very common term, you know it, is a maximum transfer unit. So the maximum size of the packet has a maximum size, cannot exceed, right? So this defines the path MTU, the fragmentation size, it has to be, right? And then other parameters in here. All right, so we understand what security association is. There is inbound, output, bound. So it's the parameters that they have to agree on. It's kind of a database, right? Now we're going to talk about security policy. What is security policy? Is it clear so far? Anybody's confused? You know? So let's talk about security policy, I think. Yeah. So it's another important aspect of IPsec is the security policy, SP, which defines the type of security applied to the packet when it is to be sent or when it has arrived. So you need to send the packet, you have to know what's the policy for applying the security. And when you receive it, you have to know what policy was used in sending it that you're reverse applying it. Okay, what is the policy? Okay, so before using the SAD, what is SAD? Security Association Database. Okay, discussed in the previous section, a host must determine the predefined policy for the packet. So the predefined policy could be there's no security, don't use security, don't use, or use. All right, policy. What is a policy? Right? Policy. You know what's policy? It's rules, right? So, for example, what is the policy for password in Google? To create its policy, right? So it has to be minimum 8 characters. It has to contain at least 1 digit. It has to contain at least 1 capital letter. It has to contain at least 1 special character. What we call this? Policy. Okay? Policy. Alright? What is a policy for you to register for next semester? You have to register for a maximum of 4 courses. Okay? And each course you have to make sure you took the prerequisites. And you have to be according to policy. There is a policy. Right? in terms of security, there is different policies. You have to apply security to provide this and this and this, or the maximum you could apply is this and that. Or policy. That's what policy. So it's kind of database that the sender and receiver has to know before they go to create the association. Clear? So you could think of policy as rules. You could as rules, right? Security association as what? As keys. Keys, like to do the security, right? So connection identification. So for example, it's a file. So you have the source address, the destination address, the name. The name could be the DNS name, right? Okay. The protocol, the source port, the destination port, and what is a policy? Okay. Okay. So SA is the source address, destination address, protocol. What are the protocols?
Authentication.
AH and ESP, right? And source port and destination port, and there is a policy. So look in here, what will happen? Okay, so Alice would like to send data to whoever. Okay, so it goes to application layer to transport layer, and the transport is gonna go to the index, similar like here. Okay, part of the data, you know, destination, right? So you're gonna see the policy. What the policy could be? The policy could be apply, or bypass, or drop. So if there is a policy, okay, either you apply, if you match, you apply, or you drop. If not, if there is a bypass, you don't have to apply it. So the data goes from transport layer all the way to where? IP layer, data link layer, physical layer to BOP. Right? If there is no policy, you don't have to apply any policy. If there is a policy, you have to check it. If it applies, if it's bypass, again, if the policy was not applied, the rule is not applied, then you have to drop the packet right away because they did not apply the policy. If it was applied, then where we go after that, we're gonna go to the outbound security association database, which is here. So you know all of these, right, from the database, right? Okay, then is there a security association? Yes. Okay, and that includes the keys and the protocol, the encryption protocols. Then IPsec layer, you issued IPsec layer, and you're gonna go to the IP header and all of that. If not, then you go to internet key exchange. You have to give the keys, okay, from the internet key exchange, right? So the first thing you have to go to the policy. Then after that, you're gonna go to the security association. Whoever confused can ask, and I can try to answer.
Why would you use a bypass? Because isn't
Because the policy, it says don't apply.
no? I'm saying if the policy doesn't make it more secure.
Sure, but sometimes you don't need to make it complex. So the policy is no policy. The policy is no policy. So it's in here, the policy. It tell you, yes, there is a policy. Then the system here has to check it. If it was applied, then you continue. If not, you drop the packet. But if the policy says none, which policy can I apply? Then I don't need any policy. Continue. All right, that's it. And go. Now when it is received, Bob, right, Bob? So the same thing. It's coming from here. It's gonna go to physical data link IP layer. Then it's gonna go to where inbound security policy. Okay. So if the policy there is a policy. If it was applied, you're gonna check it. Then you go to the inbound security association. If not, you're gonna discard because it's bad. Did not follow the policy. The sender required the policy, not use it, right? Or if the policy don't use policy, bypass, it's gonna go up. But if not, you're gonna go to inbound security association database. You're gonna search the security association. If it's there, then you apply it, then you go up. Otherwise, you discard because you don't have the key, you don't have the algorithm. Discard. You cannot do anything with it. All right. So this is like a lot of details. I mean, you're getting. I know that you are getting like 50% of what I'm talking, 60%. But once you read it, you'll understand it because you'll be able to go back and forth. Okay. So it's like, you know, it's a whole system. You know. Okay. It's exactly like when somebody asks me, how is car engine work? My answer could be simple. You put the key in the switch, you turn it like this, it will start, then you put the gear move. Can you understand this? You can. But if I need to explain, you know, what will happen inside the engine, I will have difficult time to explain it to you, right? So there's many, I could give you a general idea, but the details that you have to read it because you have to go back and forth between the pages to grasp it, right? So if you are with following me 60-70%, I'm happy. Okay.
So, can you go back to the other slide?
Here.
What's the IKA?
IK is Internet Key Exchange. So if there is no entry for this communication between the sender, you have to build it, right? So you have to go to IKE, which is the last section of this textbook, okay, to issue that.
But we don't have to go back to the IKA when it goes to the other to go.
In here, no, because the exchange or the keys starts from the sender, not the receiver, right? So if the sender does not know it, or something, yeah. Okay. So in here, Internet Key Exchange, that IKE, all right, the IKE, all right. It's a complex topic in here, okay, but I'll try to explain it in a very short because there's so many ways of doing it. So there's a lot of details. So if you can understand, you know, generally how it works, I'm happy. All right. So the Internet Key Exchange, IKE, is the Internet Key Exchange is a protocol designed to create both inbound and outbound security association. So in the previous section, okay, we presumed in our explanation that already the tables are there, the security association is there. This is already there, right? Sender and receiver, we presume is already there. Then we explain to you the policy. Then we explain to you how it will work. And we explain this, how the receiver will receive it, right? This is under the assumption that the security association is created, is already there. Okay? Security association includes what? Information, right? All of this information. They have to be shared between the sender and receiver, right? So the reality is there is a protocol to create, to share this information called IKE. IKE. Okay? So IKE creates security associations for IPsec. Simple words. For here and back, we assume that all the senders and the receivers, they have security association with each other. That means they share already the key, the encryption, blah, 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 right? All of this information. But we don't know how they shared it. That's what creates a security association. Alright? So we learned about security association database and security policy database. Now we're going to talk about how to create association. So basically, there's three components for it. Okay? Protocols designed by people for different purposes. They are used. The first one is called OCLE. The second one is called SCIMI. I'm not sure if I'm reading it right. The third one called Internet Security Association and Key Management Protocol. Three separate protocols put together created the IKE. Alright? Three separate protocols put together create the IKE. So OCLE protocol, which was here, the OCLE protocol, okay, was developed by Mr. Orman. It is key creation protocol based on DiffieHellman, key exchange method. We know what's DiffieHellman? We could create two keys and exchange them without third party. Okay, it's based in with so it's kind of DiffieHellman key exchange method, but with some improvements as well as some improvements, right? However, the second one is skimming here, designed by Hogo Rauschezek, I think, is another protocol for key exchange. It uses public key encryption. What is public key encryption? You have two keys, private and. So this is used DiffieHellman and this use public key encryption. All right. So these are protocols adopted. Okay, they work as adopted. All right. Then we have this one, the Internet Security Association. Okay, key management protocol is a protocol designed by the National Security Agency that actually implements the exchange defined in ITE. It defines several packets, protocols, and parameters that allow the ITE exchanges to take place, and in standardized formatted messages to create secure association. We will discuss it. All right. So that's what it is. Okay. So there is 5 ways. Okay. The first thing is improve DiffieHellman. Improve DiffieHellman. So DiffieHellman key exchange. So you know in DiffieHellman what we do, what both parties have to choose P and G, right? And then it will create key I for initiator, G to I, mod B. So I is a random number chosen by the initiator, and R is a random number chosen by the responder. Then they exchange, right? And then the shared key is created, right? Shared key is created, right? What's the problem with this technique? Is the middle and the man in the middle, and you know, weaknesses, some weaknesses, it could happen there. So that's what we call it, the session key between the peers, right? Without needing to a third party, right? So does it have problems? Yeah, it could have few problems, you know. So DiffieHellman with cookies, you could use DiffieHellman with cookies to prevent the clogging, okay, or denial of service attack. So to prevent denial of service attack, what we do? So we send cookie first. Cookie like the name, the IP address, whatever, you send it, and this will respond with the cookie for the initiator and cookie for the responder, and then everything after that the same. So you create the key, and then you send the key with the cookies, and every time you send the key with the cookies. So this is to prevent what? Denial of service, sending a lot of requests. Okay, so when initiator send a request to responder, let's say the initiator is a fake one, and keep sending. So the responder will be busy creating the keys. So the responder needs to make sure it's coming from the right initiator. So you send some cookie. Cookie, what is cookie? Information. It could be the address, the IP address, the DNS name, whatever it is. All right. So to protect against a clogging attack, what's a clogging attack? Like denial of service attack. ITE uses cookies. To protect against replay attack, ITE uses nonce. What is nonce? A value, like time nonce or whatever. To protect against man in the middle attack, ITE requires that each party shows that it possesses a secret. Okay? Possess a secret. Alright, so IKEY phases. There is how many phases for IKEY? Okay, there is 2 phases. IKEY divided into 2 phases, phase 1 and phase 2. Phase 1 and phase 2. Phase 1 creates security association for phase 2. Phase 2 creates a security association for a data exchange protocol such as IPsec. So let me explain this, and maybe I'll stop like there on here. So in here, what we are trying to do, trying to create a secret key between them, right? Okay, and the secret key is for security association, right? What do I need to do that? How do I need to do? How can I do that? DiffieHellman in this example, right? But at the very beginning, what I have to do? We have to, both parties have to know PNG.
How can they agree?
So how both the, I mean, yes, now if I have, so remember from the beginning we said we presume that we have secured association, we have the database already. Alright? We showed you how it works. Then after that we said, oh, now we have to tell you how to create the security association, right? So to have the security association, what do you have? Do you have the secret key? So how they create we create secret key. But we tell you, we presume that they know PNG already. But the question, how they know the PG?
Security.
We need another security. So it becomes like a loop. A loop. To create a security association, initially you have to know this value. So we have to have a security association for this value. Then becomes like a loop, right? That's the whole question. In this case, how can both initiator and responder know PNG? So we have to create a security association for it, another one, you know. And this creates another one. And you understand what I'm saying, you know? So it was done smartly that they divided in two phases. Okay, it was like building the security association gradually. So we have phase one, which creates a security association for phase two. So phase two, you know what? The PNG, and you create the secret key. Phase one, you should know the PG. Okay, you understand what I'm doing in here? Alright? Alright? So what will happen in key phase? So in the phase one, what will happen? You start main mode. There's 6 exchanges. Okay, or there is aggressive mode, 3 exchanges. So by the end of this, what I know? PNG. And then phase 2, I have a quick mode, 3 exchanges. What is exchanges? Exchanges, right? Let's take a look at one then. So the main mode or aggressive mode methods, you could have authentication modes. You could use a pre-shared secret key or original public key or revised public key or digital signature. So phase mode, phase 1 main mode, how many exchanges we're gonna have? 6 exchanges. So in case you have, let's say that you have a pre-shared key. So you create a header and security association offered by the initiator. Then you send back the header with security select. So the initiator could offer multiple keys. The responder will select and will send back. Then it will be sent back the header with the key for the initiator and NE. What is N? Nonce for initiator. Then it will send the header key for the responder, the nonce for the responder. Okay, and then we'll send the IDI. What is IDI? The ID of the initiator with the hash for the initiator encrypted with the pre-shared key, and it will send it back. So at the end, they will have the hash in here as the shared value, the initial shared value. So remember that we have 1, 2, 3, 4s, right? The second way using public key. What's public key? There's public and private key, right? The same thing. They have 6 exchanges. And then after that, digital signature, you could use digital signature key. Okay? In the aggressive mode, you save the 6 steps to 3 steps. So you're kind of increasing the messages. Alright? So that's an aggressive. I mean, I don't want to go through the details. The idea is the most important thing. Okay. Then after that, we're gonna come to the quick mode. Where's the quick mode? Which is in phase 2. In phase 2, you already have the initial keys. All right. Please go through that. You'll understand it. We don't have time. We have a few minutes. Okay. And the phase 2 will be quick mode is ready in here. So now you create the security association, which includes what? The secret key. The secret key. Alright? So there is many algorithms for security association. Modular exploring group, 5 of them. And this is for the hash algorithms. Okay? Different hash algorithms you could use. I mean, like in here. Where is the hash? So in hash, what kind of hash you gonna use? There's multiple options for you in here. MD5, SHA, Tiger, all of these. And for encryption, you could use this, Prooffish, AES, different options. All right. I will keep the ICE camp for you to go over it. Okay, we don't have time. All right, but that will be it will be the last thing. So you understand how is the general header created and killers. All right. So what we have learned. Let me go very quickly. I know we went very fast through this. Okay. So. Okay, so we started with saying that we are trying to have security at the network layer. So we have 2 modes: transport mode and tunnel mode. Transport mode, all right. We don't protect the whole IP packet. Okay, however, we protect the payload. All right, and in the tunnel mode, we protect also the IP header. We add a new IP header. Then we explained two protocols, AH, okay, and we spoke about the ESP. These are the protocols. We explained them. Then after that, we said for protection that you need to have security association, which is the data they share. All right. So it's kind of database, inbound and outbound at the sender of the receiver. And we need before that a policy. The policy in here. And then this is how the process. It starts by checking the policy and checking the security association database. And the receiver and the sender. Then we come to the point how we create the security association. How we exchange these keys in advance. Then we said there's 2 phases. There is the IKE, which is a combination of 3 protocols. All right, basically we start by using DiffieHellman or fixed DiffieHellman or different protocols. All right, but for that we need to have another security association. We need to know the initial parameters. So we created security association 2 phases: phase 1 and phase 2. Right. Phase 1, it has 2 modes, or 2 kinds. Phase 1, what is this one? Oh, that's not phase 1 here. Okay, phase 1, it could be main mode, which 6 exchanges, 6 message exchanges, and aggressive mode, 3 exchanges. Then it goes to the phase 2, which is 3 exchanges. All right. So that will give you a security at the network layer. All right, thank you so much.